hoping to talk with him, but luckily he decided that he will join us remotely. So thank you very much, Rajeev, for joining us remotely, and we are looking forward to your talk. So.
Yeah, thank you, Moshe and Rudiska. Yeah, I'm so sorry that I couldn't be there. Actually, I spent yesterday I spent like 6 hours at the airport just waiting for the flight, and eventually just after midnight it got canceled. So yeah, I had to then cancel the trip. But I'm happy that at least I can talk to you over Zoom. So I'm going to tell you about specification-guided reinforcement learning. And so reactive synthesis is a major theme for this meeting. And in the morning, I'm sure Moshe talked about it. And I'm going to tell you about some connections. And so so we know that in controlled synthesis, the inputs are an environment model and an objective. And what we want the synthesis algorithm to do is to produce a policy. Right? So in reactive synthesis, the model is given as a Markov decision process, typically like a known model. And this is more to do with a probabilistic version of reactive synthesis. And as we know, that the objective is typically given as a temporal logic specification. In reinforcement learning, the problem is quite similar, except that now the model is an MDP with unknown transition probabilities. And if you're not familiar with reinforcement learning, I'll make it more precise in a few minutes. And then the objective is typically specified by associating rewards with states. And what we want to maximize is the cumulative discounted sum of the local rewards. Right? And in fact, if you look at the definitions of reinforcement learning in ML literature, usually this association of rewards with states is built into the model. Actually, the Wikipedia definition of MDP says that the rewards are associated with states. But what we are going to do is to study reinforcement learning from the lens of reactive synthesis, where we can vary the objective. We can look at what happens when the objective is specified as temporal logic and what are the theoretical consequences. In this talk, I'm going to focus only on theory, though we have a lot of results on trying to implement some of these algorithms. So to make things precise, so let's start with definitions of MDPs and policies. And here is my simplest MDP, which will be good enough to illustrate some of the points in this talk. So in this case, the MDP has 4 states. There is an initial state, and we have 2 actions, in this case, A and B, the green. And at the beginning, if the controller chooses the action A, indicated in red, then with some probability P, the environment will transition to the top state, and with probability 1 minus P, it goes to the bottom state. In the initial state, if it chooses B, then it goes to the right state. And in the right state, actually, no matter which action is chosen, with some probability P prime, it goes to the top state. Right? So it's just an example of an MDP where you have states, actions, and then for every state and action, you have a probability distribution over the state. Right? So in this talk, we will just look at deterministic policies, the not super essential for the theorems, but then a policy is a mapping from the history of states to the next action. Right? So in this example, we actually have only 2 meaningful choices in the initial state, either choose A or to choose B. Right? And then the objective, it's conceptual, it's mathematically, it's a mapping from a sequence, infinite sequence of states, like S to the power omega, to some real valued quantitative metric. And once we fix a policy, then what we get is a Markov chain. and we can then associate with a policy an expected reward. And what we want to do in synthesis problem is to find an optimal policy, right, which maximizes this expected reward. Right? So in temporal logic, we could then specify the objectives as using logical formulas. For example, eventually goal, where goal is the top state. And now if you think a little bit about this, is that if the probability P prime is positive, then once you get to the right state with probability 1, you will be guaranteed to go to the top state. So it makes sense, as long as P prime is positive, it makes sense to choose the green action at the beginning. Otherwise, if P prime is 0, then you will get stuck if you choose the action B. So it makes sense to choose the red action at the beginning where you would achieve the goal with probability. In reactive synthesis, this has been well studied. So given a known finite state MDP and a temporal logic formula, find the optimal policy. There is work dating back to 1990s by Yanakakis and Kurkubetis, and also by Moshe, and later implemented in tools like Prism. And these are actually very fascinating algorithms. And basically, this talk is not about reactive synthesis, but just to remind you, typically what happens is you translate the formula into kind of a deterministic automaton, and then you take a product, and then you do some analysis on the strongly connected components of the product of the MDP and the Buki automaton. There is also just an aside that the automaton doesn't have to be deterministic. It's actually some weaker version of determinism, which is called good for MDP. And in probabilistic verification, there are a lot of nice results about this problem. But as I mentioned, in reinforcement learning, typically the objective is specified in a more quantitative manner by associating rewards with individual states. So in this example, if I really want to go to the top state, I could associate a positive reward, say X, with the top state, and maybe the reward 0 with all other states. And then a reward is just a mapping from states to reals. And over an infinite run, then I can lift this reward by taking discounted sum. So gamma is a discounting factor, and it's between 0 and 1. And what gamma says is that getting reward today is much better than getting reward tomorrow. Also, if gamma is less than 1, then if I take this cumulative sum, then it's guaranteed to convert. So the reward, the infinite sum is well defined. And in this example, so if we have associated positive reward X with the top state and reward 0 with all other states, then the expected reward of the red policy, like choosing A at the beginning, would be something like P times X. Well, actually, the infinite sum, like X plus gamma X plus gamma square X, and so on, because once you get to the top state, you just stay there. But roughly it's P times X. But for the green thing, if P prime is 0, then you won't get any reward. But otherwise, you will get about gamma to the power n times X, where gamma, because where n is the expected number of states that you would need to reach X once you are in the right state. Right? So the probability to go from right to the top state is P prime. So if if the expected number of steps that before you hit the top state is n, then your reward will be discounted by gamma to the power. Right? So when I know the MDP, then actually you can optimize the discounted sum. And now the algorithms here are a bit different compared to the analyzing SCC's type of algorithms that are prevalent in analyzing temporal logic objectives. And this is a well-known algorithm called value iteration, where you initialize the expected value of the objective in every state, and you iteratively update it depending on by looking at what would happen if in state S, if you choose an action A, and you use the previous estimates for the rewards in all other states, and how would that objective change? And you keep doing this update till you converge, right? And again, this is a well-known algorithm, so I won't go into the details, but it's there on this slide. Right? So now let's switch to the reinforcement setting. So the previous algorithm value iteration was to find the optimal value for the discounted sum reward, but assuming that all the transition probabilities are known. But the key difference between reactive synthesis and reinforcement learning setting is that we are assuming that the probabilities are not known. Actually, the rewards are also not known in advance. And the learning algorithm interacts with the world, it interacts with the MDP, and then learns these transition probabilities. So for example, going back to our previous example, the algorithm knows in advance that there are 4 states and there are 2 actions available, A and B. And the MDP starts in the initial state. But if I apply an A, it doesn't know what the probability is. So when we execute the algorithm, the learner gets to propose an action, let's say A starting in the initial state. And what will happen is that the environment will change its state depending on what the underlying probabilities are, which are not known to the learner. And maybe the state will get updated to the, say, the top state, and then the learner will get to propose another action, and the game will go on like that. And at once in a while, the learner can also propose to reinitialize the system by resetting the state to the initial state, so that it gets to again see the effect of applying A in the initial state. Right? So at every step, the MDP is in a particular state, and the learner can either choose an action, and the MDP will update the state by sampling the next state according to the underlying probability distribution, or the learner will reset the state to initial state. And at every step, if the user could stop this process and ask the learner to output the optimal policy. And based on the history, the learner can estimate the transition probabilities. And then the best we can hope for is that the policy it outputs is epsilon optimal, because it doesn't know the exact probabilities. But one could assume that it has run long enough and has good estimates of the transition probabilities. And then the policy it outputs is a good approximation, epsilon approximation in the sense of approximation algorithms of the optimal policy. So the precise definition of learnability, I'll tell you in a minute, but when we don't know the transition probabilities, the value iteration actually can be modified to an algorithm which is called Q-learning, which it's basically some modification of the value iteration, but now since we don't know the transition probabilities, we are keeping an estimate of the Q values at every step, and due to lack of time, again, I'm not going to go through this algorithm. This is a classical algorithm, but the main point is that the value iteration algorithm for discounted sum can be modified with some small modifications, can results in an algorithm which works for MDPs with unknown probabilities. Right? And the precise property of Q-learning and similar algorithms that we want is that just based on the number of states and the actions of the number of actions of the MDP, if I want to say that I want like an epsilon approximate policy with high probability. Why with high probability? Because the algorithm itself is randomized. At some points, it could, for example, decide to reset the state, or it could either choose an optimal action based on what it thinks so far, or it could do exploration by proposing a completely different action so that it gets to see more of the MDP. So the algorithm is probabilistic, and the precise definition then is that there is a function which which is dependent only on the number of states and actions of the M, and these two parameters, P and epsilon, such that if we run the algorithm for those many steps, then it will output at least an epsilon optimal policy with high probability. Right? And this is called a PAC MDP guarantee. Right? And actually, if efficiently learnable would just mean that the number of steps that we need is a polynomial function of all these parameters. And there is a nice, beautiful result that this learning algorithm that I just talked about is actually an has efficient PAC learnability guarantee. So this can be lifted a little bit to reward machines. So here the rewards were associated with states. And if we want to associate history-dependent rewards, then instead of associating rewards with states, I could design a monitor. So now this is very much like the automata or the monitors that we see in our reactive synthesis community. So here the monitor could be watching what's happening in the MDP. And if I want to say that, first achieve goal 1 and then get to goal 2 and then you get some reward, then I can design a two-step automaton like this, where I get a reward only after goal 2 is satisfied. And now the rewards are associated with the states of the automaton, and this is kind of independent of the MDP itself, right? And the Q-learning algorithm for discounted sums actually generalizes with this also. And this idea was introduced in RL literature by Alur in 20. So when we so going back to this temporal logic specifications, so there have been some results, but let's try to understand this problem more fundamentally. That what would happen if my objective is specified using temporal logic, and I want to design an RL algorithm where I don't know the transition probabilities in advance. So a natural thing to do is to combine the two strands of research I just explained and try to see if temporal logic specs can be reduced to discounted rewards. So going back to our example, if I want to get eventually to the top state, then if P prime is positive, then I want to choose green, right? And suppose now I don't know the transition probability, so I want to associate rewards with individual states and apply the RL algorithm out of the box. Then I could, the natural thing to do is to say that, well, since I want to eventually get to the goal, let me associate a high reward with goal, and let's say for now 0 reward with everything else. But now it's a discounted some reward, and the analysis that we did tells us that the red policy is optimal based on its values about px, and can compare it to the green policy whose reward is about gamma to the power nx, where n is the expected number of steps that I would need once I get to the right state to get to the goal state. Right? But as you can see, that if I want to do this translation, then I need to figure out the discount factor and x in advance without knowing the actual probabilities p and p prime. But once if I design set x and gamma to specific values, then I could choose p and p prime to some values, so that in some cases red is the right policy, in some cases green is the optimal policy. Right? So that becomes a problem, and there are no values for which this translation works. And we could show that in fact there is no reduction from temporal logic specifications to discounted rewards. So the more natural translation I showed, which was associating a high reward value to the goal, one could then ask various questions. Can I associate some arbitrary rewards with other states? Can the rewards be history dependent? And what we formally show that a reduction is actually not possible. And the intuitive difficulty is that the optimal choice for the temporal logic specification is influenced by the structure of the strongly connected components, like which of these probabilities p and p prime are 0 and which are non-zero. And or if you think about how the correctness of the RL algorithm is defined. So it's at every step, it's proposing a new action and it sees the new state, and it can keep on proposing new actions. But when it outputs an optimal policy, it has to be consistent with any MDP, and for which the run it has observed is consistent. And you can always choose this make this probability small enough so that for a large class of MDPs, the runs seem consistent. And now that becomes a real problem, right? So here, one of the key contributions was actually just formalizing this notion of sampling-based reduction. But then you could ask the question that instead of trying to reduce these, the temporal logic specifications to discounted rewards, let's just think about learnability, right? So, which is the basic question: are these objectives learnable, right? And so we have in 2022, actually, two groups showed this independently, and the theorem says it's an impossibility result. Says that there doesn't exist a pack MDP learning algorithm even for safety specifications. So something like always safe. So this is to me, actually, I'll show you the proof. It's not that complicated, but it was a bit of a surprise because I think dating back to 2013, there have been a lot of papers about RL for temporal logic specs, but people hadn't really looked at this very fundamental question. Right? So in the next 2-3 minutes, let me try to give you the sketch of this impossibility result. So here I have 3 states, and the purple states, the bottom states, and my spec says that stay within this, right? And in this example, delta is a small number, it's like a parameter, that once I get to the right state using action B, then with probability delta, the machine will go to the unsafe state, right? So here the optimal strategy is basically choose A. As long if for any positive value of delta, it's highly suboptimal, not even epsilon optimal to choose B, right? So you have to choose A. A kind of symmetric version of that is that if I choose A in the left state, in the initial state, with if some probability delta, if I go to the unsafe state, then my optimal policy is going to be choose B. And doing anything else is not going to be even epsilon optimal, right? So there is no strategy that's epsilon optimal for both these two MDPs, which look a bit similar. And the main intuition of the proof is that if you don't know the probabilities in advance, like after applying A to the initial state, exactly what's the distribution. I don't know that in advance, right? So I'm only sampling. So the two are going to look observationally pretty much the same. I won't be able to distinguish between them, even if I run the algorithm, the learning algorithm, for a long time, right? And the precise proof is that now let's look at another MDP where neither from the left or the right I go to an unsafe state, right? And if we assume that there is a learning algorithm which has this pack guarantee and it works for the objective always safe. If I execute that algorithm on this MDP where the rightmost MDP where you never go to the unsafe state, then, well, if it's a correct algorithm, after a certain point, it has to output only epsilon optimal strategies because that's the definition of what it means for the pack guarantee. But then you can argue, you can show that the execution based on which this algorithm has made this decision is possible in both the left and the middle MDPs, right? And the previous slide, I just argued that the optimal strategies, even the epsilon optimal strategies for the left and the middle are disjoint. And so that gives us the proof by contradiction. So how do we address, so what are the solutions to this lack of learnability, right? One possibility is you set the finite horizon, and I know Moshe gave a talk about, LTL over finite words, but here actually I want to make highlight this key distinction. It's like here the horizon is fixed. So I say that execute only for capital T steps or H steps where I know that horizon in advance, right? Yeah. So, so actually there is a theorem which says, not just for temporal logic, if my objective function just said that, the objective function just depends on the first H steps of your execution, then it doesn't matter how complex that function is, we get learnability. But more usefully, we have papers in a couple of NeurIPS over the last few years where we proposed kind of some version of LTL over finite horizon using eventually and safety and choice and combinations of those. And the benefit of, so there you get learnability. Assume that this horizon H is known in advance. And the benefit over existing methods are that you can exploit the structure of the specification to get better learning algorithms in terms of data complexity. In CAB last year, we also had a nice result which showed that the discounted temporal logic, which was proposed in a different context, is also learnable. So what's discounted LTL? So here, if I have eventually goal, let's suppose that eventually is parameterized by a discount factor lambda. Then if goal appears, the first step where goal appears is, say, n, then the quantitative value of the specification eventually discounted with lambda goal will be t to the power lambda, right? So you can nest these. So for here the spec says that always discounted with lambda not collision, and then eventually goal 1 and eventually goal 2. So in this discounted version, every operator like eventually and always has to be discounted. And the constructions become super complicated, but the bottom line is it's learnable. It also turns out there is like this very nice result, more abstract, less computational, but also developed by Michael Littman and Mike Carbon about learnability of continuous objectives. And so let me tell you what a continuous objective is. So intuitively, an objective is uniformly continuous if its value on an infinite execution can be approximated by considering only finite prefix, right? So more precisely, it's uniformly continuous if for every epsilon, there exists a finite horizon H, right? Such that any two infinite executions which agree on the first H steps, the values of the objective on those two infinite executions will be epsilon close, right? So if so, the intuition here is that if you tell me I want epsilon optimal policies, then I can compute some finite horizon value H, and then it suffices to just look at the first H steps. And then by combining this with the result that if the objective depended only on the first H steps, it's learnable. You can combine these two ideas. And what they show is that uniformly continuous objectives are PAC learnable. And this is a paper in last year's AAAI. So yeah, I'm at the end of my time. So I talk only about the theoretical foundations of learnability, but we understand the theory now a lot better. In terms of applications, so in robotics, actually, as many of you know, temporal logic is actually very popular in these robotics conferences for using reactive synthesis, and many times there is like a session on that. So, and then while reinforcement learning is also very popular in robotics, but the difficulty in applying reinforcement learning is on long horizon tasks, the RL algorithms do quite poorly. And the opportunity of using logical specifications more from the practical side is that the structure can be exploited to do planning using the structure of the specification and then combine it with some low-level RL algorithms to learn individual control policies, right? Yeah. We are also working on what happens if predicates that appear in the temporal logic specifications are, instead of labeling states with these predicates, what we are learning it using a perception. So if a spec says eventually boiling water, well, what's the concept of boiling water? So I could teach that by just showing some examples of boiling water. So this, and we are working with some robotics people on this, and so those are like more practical directions. So thank you.
Okay, let's thank the speaker. Other questions? Okay, and this time, please definitely use the mic.
Thank you, Rajeev. Can you hear me?
Yes, yes.
So I missed here. So for safety, you showed that you cannot learn epsilon optimal policy. What about just reachability?
Yeah, no, for reachability also. Yeah.
Cannot also for reachability. That what
No.
is stated in the talk, or it follows?
No, it was not stated in the talk, but yeah, it's a similar proof works for reachability also. Yeah.
Thank you.
So reachability, where you don't know the bound, right? Yeah. So it's a very similar proof. Yeah.
Thank you.
Thank you.
Maybe this is more of a clarification question. So can you hear me, Rajeev?
Yes, yes, yeah.
This is more of a clarification question. In the definition of packed learnability, do you have dependence on the probabilities as well? Something like smallest 1 over smallest transition probability or something like that, or not?
No, that's very crucial. Yeah. So the definition of learnability is classic. I mean, it's from classical learning literature, where the function actually does not depend on does not depend on the problem, right? Yeah. So here the function h depends on number of states and actions of the MDP, and then p and epsilon are parameters of what guarantees we want. So we are trying to compute epsilon optimal policies and with high probability, and so here p is the we want the algorithm to be correct with high probability. Now, implicitly in your question was what happens if I say that whenever a probability in the underlying MDP, when it's non-zero, it has to be at least say delta, right? And I know this parameter delta. Then things are learnable, and then the number of steps that you would need to learn will depend on that value delta.
Okay, thanks.
So this was the question.
This was the question that.
Okay, so we are a little bit already over time. So let's thank Rajeev once again. And really sorry that you couldn't be with us, Rajeev. And
Thank you.
I've seen that the next speaker